I will tell you, either way, either method works on these, but one is definitely easier than the other. I don't know if that's
Well, I think
necessarily
that
true.
depends on how good you are.
Yeah, that's a good point. Yeah, because some might really like, yeah, so. Yeah. It's all relative. Come on, Noah. Nice, buddy. Oh, you're not. You're doing.
Are we rolling them together like that's the region bounded between them?
Yeah, so it's this region right here,
Oh, okay.
Oh,
not included. Even though this is an axis of like revolution,
Yeah.
it's not a bound.
Wait, does that?
Wait a minute, I'm confused. Am I missing something? Maybe I am.
well, it's y equals 0, wouldn't that make it the bottom? Amy?
Oh, excuse me. That is my fault. X equals 0. Sorry. Thank you, guys. Now we're good. Yes. X equals 0.
Yeah, but then, like the judge just pointed out, with the y equals 5, you're cutting off the top area.
This is amazing moments in mathematical educational history. Yes, this is, I need to be, dismissed post haste. Holy, what the? Thank you, guys. What else is wrong? Anything else? We good? I mean that actually, yes. Are we good? Oh, cow. I can't.
Good. That's gonna be like 7:21. Just the workstations, do they like dismantle deep to do it like that? I guess it's like deep like the ground. And it's rolling like the exits. Or could you use the shower? I don't know, yours just had,
I think it was in the shell section, so maybe it's not.
just like choose which one.
Oh.
I just did shell.
Yeah. All right, Bella. Thank you. Thank you. You good? Are you ready?
Oh, it's just like one. But I mean, it's just under that axis.
That's number 14.
But
Did you get that?
the book said there. Oh, no, I don't know. Just
Okay. Yeah.
And then can you find them? Yeah. And then I like messed up mine, but there's the ones that do X. So then I do
Gotcha.
but yeah. Excellent.
Gracie, you ready?
I was trying to do shelter. I can't find the light.
Yeah.
I think it's to do wash number, but take the stuff out of pieces. Take out some of this.
I don't know if they understand what.
It kind of looks like a sheet of salt.
Very good.
Sorry, it's maybe.
Okay, so for-
Like, right?
That's like,
I'm trying to
just
find
just-
and then subtract the inside part, and then subtract the outside part. It's just so much work.
You like a plan, like find the cylinder and subtract. Yeah.
Are you guys seeing some of the problems with like using shell and stuff?
Yeah, you really.
It's like suddenly you're like, wait a minute, these are two different curves. Yeah, so if you have two different curves, you gotta split it.
Wait, which one is that?
Oh,
Or no.
like split it.
It's-
Like,
Into two separate, like for shell going around 15.
yeah, yeah.
That's like have two separate.
Can you do shuffle?
Does that make sense?
Yeah. Okay. And I think I got that one.
Yeah. Neither,
So you have to split it up with like two.
Yeah.
Two different shells?
A shell for me would be
easier.
Yeah, that's what I thought.
Okay.
For why?
And you limit it.
What- For shell, I understand how, why is
Yeah.
just 15 minus, like,
Right.
sorry, the radius
Yeah.
is just 15 minus
Yeah.
y. What I don't understand is if you have the two curves on top of each other, how to find the length of it.
Yeah.
Oh.
That's like the upper part.
So
I
the length
see.
in each case would be
Right.
close.
Yeah.
Mhm.
But from 0 to 2, you have to use the root for your x.
Okay,
And from 2 to 6, you use the negative x over
so you just
6.
split it into like a piecewise
Yeah.
function?
It's not even piecewise,
Or not
two
piecewise,
separate
but
intervals.
like two separate, okay.
0 to 2, and 2 separate.
Oh, it's the same. Yeah.
So wait, which one does shell not work on?
Well, shell works on either one.
Okay.
Yeah, you can use shell, just wash over it as well.
How do you know when shell does?
There's a hilltop or a valley. Because a hilltop or a valley will cause a conflict with either finding the length of the pipes, or if you're trying to do outer minus inner with the washer, it's the same curve. That's the issue with that.
Okay.
But on this, you'll notice there's no hilltop or valley. But it does transfer from one curve to another, right? As you talk about like the links for part A, the links of the pipes.
Yeah, that's what was tricky.
And that is the tricky part, right? Which is one of the reasons I wanted to give you this problem. Because if I give you the choice between the two. Sometimes the hardest to start actually working.
Yeah, that was one of those, I should have done the other.
But that's okay. It's still good practice, right? Either way, it's still good practice. You guys need a couple more minutes? If you're stuck, then no would be the answer, but what do you think? Anyone want more time? Are you generally stuck? Okay. Jackie, you want more time or?
No.
Okay. No, thank you. Very nice. All right, let's do it. So how about this? You guys want to do both methods for each one?
Yeah.
Why not? So if you're going around y equals 15, it doesn't matter whether you use washer or shell, you're going to have two integrals for both, for either method, right? So let's do washer first. Sound good? Okay, so if I do washer, remember it's just outer minus inner. Will washer, Victoria, be dx or dy?
Yeah.
Dx, perfect. Everybody seeing this? Also, is everyone seeing that it's washer? Are we good with that? If you're not, please let me know. So if I'm using washer, remember washer has rectangles that are perpendicular to the axis of revolution, right? So that means your outer is going to go from here to right there. Don't go all the way down here, right? You already have more volume than you need. It's just to the far side of the shading area, right? Okay, Colin.
Yes.
This is going to be pi. We already know this is dx, right? Integrating from where to where?
Think 0 to 4.
Beautiful. Everybody okay there? Low x to high x, right? All right, cool. Grayson, what is this measurement? What is this right here? I love it. I'm just going to write it like that just for a second. Do you guys agree it's the difference between two y values? y1 minus y2. dx problems, right? I'm going to use root x. Does everyone see why we're using root x?
Yes.
It's going to that curve, right? This y minus this y. This y is variable, right? So you got to use this. Very nice, Grayson. Very nice. We all good? All right, Tim. The inner, right? The part I got to get rid of, the excess area, volume rather, is that. What's that?
That's gonna be 15 minus negative x plus 6.
Again, it's 15 minus y. It's just a different y, right? You're going to now the upper curve. Setup only, that's it.
That's much easier.
It's not bad, right? Plus, you've been doing it longer, which is part of why it's easier, right? You have been doing it longer. Any questions on this? Okay. Now, if we're going to switch to shell, right, or decide to do it with shell, they have to be parallel to the axis of revolution, right? That means it's looking like this. And I'm not going to draw these in just because it gets really messy, but these are going around here, correct? In these really, really wide pipes. They're really short. Do you guys see the problem here? These pipes get longer and longer and longer to right here. Then they start getting shorter and shorter and shorter again. Everyone see that? So I've got to break this up into two. First, I'm going to go from 0 to 2. Then I'll go from 2 to 6. Because everyone sees that this is a dy problem. Is that correct? Okay. So I've got 2 pi dy plus, in this case, 2 pi dy. Does everyone see why I'm adding them together, right? It's the volume of the outers plus the volume of the inners. Okay. Everybody good? So this first one, again, goes from 0 to 2. Second one goes from 2 to 6. Love it. Love it. Love it. All right. So now let's get the radius. Lindsay, you were talking to me about the radius before, right?
Mm-hmm.
Again, these are going around here, right? So isn't the radius just going from here to right there? That is my R. What is that?
15 minus y.
15 minus y. Now, by the way, isn't it still going to be 15 minus y, even if I've got it up here? But the difference is these intervals of integration. That's what makes the radius different from one to the other, right? So this is also going to be 15 minus y. And there's nothing to change out. This is a dy problem. I am good to go. Victoria, you okay?
Yeah.
Okay, perfect, perfect. Now all you got to do is get the length. And the length is really why I had to split it into two, right? So Juliana, what is this? It's not, it's root.
Oh,
X.
it's just X.
It's just X. Perfect. I know it's really tempting to say this is root X. If you do, you're saying this is Y. That's not Y. This is just X. Again, that's why that drawing I had on the board is so, so important, right? This is nothing more than just X. In fact, isn't it going to be X even when I'm up here? Still going from the Y-axis over. The difference is going to be the curve that it goes to. So Jackie, what is this X?
Y squared.
Love it. Julia, what is this X? Yeah, Connor, help me. What is this X?
It's 6 minus 1.
Love it. It's this equation right here, Julia, solved for X. So it's 6 minus 1. That help? Cool. How are you doing? You're good, Chase, right? Yeah. you're
So
good.
anytime there's a hilltop or valley, you have to break it up for the shell method?
Well, I wouldn't consider this a hilltopper valley. So the hilltopper valley is actually going to preclude one of them from working, right? You really won't have a choice. Well, you have a choice. It's a false choice. Okay? So if you had something like this, it's kind of the drawing I had in the yesterday, right? In the notes. Let's say you were going around here. I think we talked briefly about the fact that maybe you should focus in on the one that doesn't work, which will help you get the one that does work. Which one will it be, vertical or horizontal rectangles that don't work here? It'll be horizontal. So anything that uses a horizontal rectangle, you can't use, right? Which means if you're going around here, Bella, which one will you use?
For that one, you would have to use the,
So I'm locked into having these, correct? Which method is that in this case?
if you're going around the,
The y-axis.
oh, then that would have to be the, shell method.
Awesome. Does that make sense? Okay. Yeah.
Y can't use.
Here's why. Because remember, to use a horizontal rectangle, in order to get this distance, it ends up being the same curve on either end. And that's the issue. How we doing, people? We good? Which means if I go around here, sorry, we might do both of these. Let's say I go around here, I couldn't use the shell. I'd have to use washer. Okay, Victoria, I hope that helps, does it?
Yeah.
Okay, beautiful, beautiful, beautiful. All right, so let's go on to 7. X is equal to 7. The same type of conflict. I think I'm going to start with shell here because I think shell is easier. Right? So if I'm using shell, here we go. Ding. Cat, dx or dy problem?
Yep.
Dx, beautiful. 2 pi dx going from where to where, Cat? 0 to 4. Beautiful. Partial credit. Love it. All right, here we go. Connor, radius is from here to right there. What is that?
That's just, oh wait, no,
Take your time. Take your time.
4 minus X.
Close.
Oh, 7 minus X.
Got it. I can leave it. It's a DX problem. Good to go. All right, Bella, how tall are they?
Would you have to subtract the lower one from top one?
You got it.
So then it would be, negative X plus 6 minus root X.
Beautiful. How we doing, people? We doing okay? Love it. That was way easier with shell, right? So with then washer, we have a drag. All right, again, we have the same kind of issue that we had when we were going around y = 15, right? Tim, you doing okay?
Yeah.
Okay. You sure?
Oh, yeah, I'm covered now.
Love it, love it. Okay, so as I go around here, right, if I'm gonna use washer, I got outer minus inner. I can narrow it down actually to 3 intervals. Do you guys see how I'm gonna do this? If I do the outer, I can go all the way from 0 up to 6, can't I? Because it's the same curve, basically at a constant radius, right? So if I do the outer, you guys agree if I stand here and I look to the far side, the nice thing is bottom to top, it's always the same curve here. Cool, so let's do that. This is gonna be pi. Integrating from where to where, Grayson? Because it's a dy problem, correct? Beautiful. What is that radius there?
outer.
Yep.
Oh, 7.
Good. I don't know why I made that space so huge. 7 from 0 to 6. Square root dy, you're good, crazy. All right. I can relate this morning. Kidding. All right, now here we go. The inner, right? So now the inner is going to be defined by this curve going from 0 to 2. Then the innards are going to be defined by this curve as they go from 2 to 6. Can you guys see that? The inner curve, right? If I do outer first and then inner second, because remember, it's all about me standing right here on the axis of revolution. For the outer, I look to the far side. For the inner, I look to the closer side. But the closer side is defined by this curve from 0 to 2, and then this curve from 2 to 6. Is everyone okay with what I'm saying? Okay, perfect. So I'm going to take away that pi. Let's go 0 to 2 first. dy, Marina. What is that?
7.
So minus x. Can't have an x, it's a dy. This is going to be y squared. Yeah, Paul. Colin.
Yes.
I'm also have to take away then pi going from 2 to 6 of dy. What's this?
Another 7 minus x would be 7 minus plus y plus 8.
Is it 6 minus 1?
Yeah.
Is that right? Okay, good. Thank you. Nice to be Colin. We're all good.
Why did you have the third segment?
Third segment is because remember, I've got two different inner sets of coins, basically. That going from here to here, and then the inner coins go from here to there. That's what this is. Yes, Jim?
Why don't you put like the second 2 in parentheses and after?
You could.
That's not the same thing?
Yep.
Okay.
It's your baby.
Is it okay if we leave it like that
Yep.
and don't add them together?
Yep. Got it. Really similar to like breaking up a log, expanding a log, having two things in the bottom. You could minus the sum of the bottoms, or you could subtract them each one. Doesn't matter. All right, people. How about this? I think I want to get to the notes, and then I'll do a question. So if you guys don't have questions, you can just start working on that. I need about 12 to 13 minutes. Okay. So it's very, very closely related to what we've been doing in 6.2 and 6.3, but it's not. It's different because there's no revolution. And it takes a little bit to get your head around this. No, it's okay. It's okay. You guys, we're good. We're period 1. It's hard to draw. So if I'm losing you, if you're like, I have no idea what you're doing, please just tell me. All right. All right. So this is called volumes of solids with known cross sections. And we're going to be generating like volumes of shapes for which the base shape is defined. This is 6.2 volumes of solids with known or given cross sections. I know. It's a little abstract. So check this out. Let's say that I have a solid sitting on like my desk, like just a decorative piece sitting on the top of my desk, right? I'm going to give you the curves that trace out the base of the shape. Okay. So like it might be two known curves, something like this. Like let's do y is equal to, sorry, that's wrong. Let's do x squared minus 2. That's wrong. X squared minus 1. Sorry, guys. Sorry. Y equals negative x plus 1. So this will be the base of the shape, all right? Something that looks like that. So as I set it on my desk, that is the base of the shape. So now what I want to do is, I'm going to kind of look at this three-dimensionally. So I'm going to try to draw this three-dimensionally, okay? I'll just start there. You guys with me? So that's kind of like my desk. I'm standing back from it a little bit. That's like graph paper sitting on my desk, three-dimensionally. Right? I'm going to draw these two curves. Not perfect, but try to get the idea. So that's my parabola. Then I've got a straight line coming down through it. Okay. So the known cross sections come into play now. So what's going to happen is I'm going to tell you what shape the cross section is. And the cross sections are going to be taken perpendicular to the x-axis. That means if I take this solid sitting on my desk, and this is the base, let's say I have, for instance, square cross sections. What I'm going to get is I'm going to get these square shapes. Like if I took a knife and I cut this shape sitting on my desk, cut it like this, and I take the two sides and I look at them, I'll see squares. So the cross sections are squares. So let me see if I can draw this three-dimensionally. Let's say I've got this right here, this green segment, right? I've got this square coming off my desk. That green is like the top of the square.
So it's pretty much the same base on the top and then just parallel line.
Right. So check this out. Let's say I drew it here three-dimensionally. It's going to look something like this. With this green top. Can you guys kind of see that? I have a square coming off my desk. The farther apart the two curves are, the taller the square will be. It's really hard to draw this thing like, you know, the complete shape three-dimensionally. But do you guys kind of get the idea of what's happening here? If I take a square right here along the x-axis, I end up getting something that looks like that. And then that's the green top right there. Yeah.
So is the top like variable?
It is variable for sure, for sure. So what you're going to get is you're going to get something that kind of looks like this. It's like a squared off slug, for lack of a better term. But it definitely has two distinct ridges that define the top corners of the squares. I don't know, should I draw one more? I don't know if this is helping. I don't want to confuse everyone. So I got this square coming off my paper like this. So over here, it's going to look something like that, right? And the closer it gets to the side, it's going to get shorter and shorter and shorter until it comes down to a point, basically. Okay, visualizing the entire, yeah, it's kind of like, you know, like that.
It's just like the same as our shell or washer stacking, it's just squares.
It's just different, yeah, it's just square. That's exactly right. Yeah, go ahead.
They are squares, right? So
They are
the
squares.
height is gonna change.
The height will change. That's exactly right, Victoria. And interesting too, Julie. Look, the farther apart the two curves are, the taller the squares will be. This is the same as the height, right? So here's how to do this. Rather than just get caught up in like what it actually looks like, here's what I'm going to do. I'm just going to draw one of these squares. It's not a square. Let's imagine that's a square, right? All right. And what I'm going to do is just focus in on that volume, right? Because what I'd like you to think about is this being is like a series of books, all of different sizes, just stacked against one another. Yes? So I'm going to do a finitely wide book, and I'll use the magic of integration then to make them infinitely thin books. The thinner the books are, the more close to the actual smooth shape I'll get, right? It's exactly like disc and washer and shell, right? So I just have to focus then on the volume of this sucker. And do you guys agree that it's just length times height times width? And width is dx. You guys agree? Look, they're all infinitely thin, right? Dx means super, super thin along the x-axis. So this is going to be dx. So let's talk about this. What is this? Isn't this the green length? How do you find that green length? Spectral-wise, top curve minus bottom curve. Isn't that basically what finding area is? Top curve minus bottom curve. So here we go. I just build that in. This is going to be, negative x. Something. I'm telling you, I got my D game going today, guys. That's negative x plus 1. So this is negative x plus 1 minus x squared minus 1. This being my length. Grayson, you okay with that? Okay, so it's upper curve minus bottom curve. Just using parentheses rather than changing the signs. You guys with me? How about the height? What's the height?
The same thing.
Same thing. Lindsay, integrating from where to where do you think? Oh, let me put in some points here. I think this is negative 3. This is related to 0. Go for it.
-3 to 1.
Thank you. So look, guys, if you had something like this, you'd have to FOIL this out, simplify this, then FOIL it out, right? Plug in 1, plug in negative 3, and subtract in that order, right? Again, on the quiz on Friday, I'm probably not going to have you do this. I'll probably just have you set it up. I don't want you taking 15 minutes to integrate. It's not worth it. Yeah.
So, real quick, if we were to look at the flat line, the negative x plus 1, it would look like a parabola, that same parabola flipped up.
One more time.
Okay, if we were to look at the flat edge.
Yeah, this flat edge right here. Yeah.
That 3D flat edge, like,
Uh-huh.
you don't have from this angle.
Yeah.
It would be the same arc as flipping up that x squared minus 190 degrees relative to the whiteboard. So going from this to that.
No. The height of that shape is based only on the distance between the two curves.
Yeah, but the distance is going to be the same on every parabola to the.
I see what you're saying. So you're saying flip this up like
Yeah,
that?
there we go.
I'm with you. Yep. At least on that edge, right?
Are we only doing squares?
Nope. I just want to make sure we're good here. Can everyone kind of visualize what's happening? Okay, good. Let's keep going. What if I said, hey, let's make them not squares, let's make them semicircles. Here's all you got to do. Every single time it goes back to the volume of one of the books, right? Now I have a book that looks like a taco. Thanks, Julie. All right, so what's the volume of a taco? Yes. Uh-huh. Area of the base. That's how wide it is. Super, super, super thin. We already know the width is going to be dx, right? Okay. Gotcha. All right, here we go. So, hey, partial credit. Come on. Now, check this out. All you got to do is get the radius, right? Isn't it true that the radius goes from here to right there, which is here to right there? What is that?
The length divided by
Length divided by 2. What's the length? Easy. Negative x plus 1 minus x squared minus what the? Minus 1. All that over 2 squared. Whoops. Thanks, Lindsay. I'm telling you, today's a train wreck. And it's only period 1 though for me. Good. So radius, right? Half the length squared pi times how thick it is, that is dx going from -1 to 3. How we doing, people? We good?
How did you choose which one to like subtract? When you took -x plus 1
Yep.
minus, how did you choose the order?
Upper minus lower.
Also, is there still a 1/2?
Excuse me.
Okay.
I'm telling you, see? At least I'm consistent. Every problem's gonna be wrong from here on out. That's exactly right today. You got that. Oh my goodness. 7 minutes. Grayson, what's the matter? Okay. Let's do another one. What if I did equilateral triangles?
Then we would vote in a heck.
Yep. Turn it in and say, I'll take the 0. Equilateral triangles. I'm not redrawing them on my 3-dimensional picture, but, you know. Got to focus on that. And something like that, right? Okay.
What did you use, Mr. Carver? Are they nachos?
Yep. Thank you. What's the volume of that sucker?
They want Mexican.
What's the volume?
Base times height, whatever.
Volume is equal to 1/2 base times height times how wide it is. Dang it, but that's okay. I'll be consistently inconsistent.
You asked,
Inconsistently consistent, whatever, who cares? Yes, Colin.
would you ask questions like, what is the volume of this if you're using semicircles?
Yep.
Or like,
This is gonna be different every time, isn't it? All right, cool. Here we go. Here we go. I'm gonna go from -1 to -3 to what? dx, perfect. I got a half out front, partial credit. Love it, love it, love it. All right. Let's talk about the base. Do you guys agree this is the base? Same as that. What is that? Anyone? Anyone? That's right. Top curve minus bottom curve. What? Top curve minus bottom curve. How we doing, people? We all good? Okay, I'm gonna take you back to geometry. We got this. A equilateral triangle is a 60, 60, 60 triangle, correct? Okay, because here's what I need. I need this. That's height, right? I got a 90, 60, 30, 60, 90 triangle, right? 30, 60, 90 triangle. Isn't it true? They are in the ratio of 1 to square root of 3. You guys remember this? All similar triangles, right, are 1 to square root of 3. That's where like the ratios come from for trig, right? So this is going to be 1, 2, square root of 3. How we doing, people? We good? All right, good. By the way, don't forget 2 is the hypotenuse, right? It's bigger than square root of 3. Look at those backwards. Easy to do. So now check this out. Isn't it true that the height of this rectangle, the height of this triangle is equal to root 3 times whatever this is? Let me say this one more time. So if this is 17, isn't this 17 root 3? Well, what is this? No.
This is negative, it's
Oh,
with
right.
divided by 2.
Awesome. It is this divided by 2. You guys with me? So I'm going to put this in here. I'm going to do negative x plus 1 minus x squared minus 1 all over 2 times square root of 3. Right? So like here's my 17. This is 17 root 3 for the height. So I got 1/2. Here's my base. All of that is my height, and this is my width. Yeah, Jason.
would we take the 1/2 out here in this case?
Yeah, you could, absolutely. In fact, you could take the root 3 over 2, so it'd be root 3 over 4 all the way out to the front, right? You just have this thing squared, basically.
So like the 1/2 in front, since we're not using both base and height of the triangle.
It doesn't matter. we're still calculating the area of a triangle, so it is 1/2 base times height times height.
So we could take, we make the entire formula like √3/4
Yep.
integral base squared.
Yep.
Times dx.
Perfect.
Much easier.
Especially if you're integrating it all, right? No doubt, no doubt. Real quick. Let's say you had a circular base. Circular base, radius of 2. Let's just go back to squares really quick, just so I can set this up, okay? Because we're running out of time. Let's say I've got square cross sections. Right, so this does something like this. Right, cool. So I'm going to, again, just focus on that volume right there. And it's going to go from -2 to 2. You guys agree? Because these are books all stacked against one another. I just have to have the base. The base goes from here to here. Here's kind of the problem, people. Do you agree? I have the same function on the top and on the bottom. So I can't do top minus bottom, otherwise I get 0. Everyone with me? So I'm going to use the fact that this is symmetric to the x-axis. I'm going to double this value right here. What is this? Just from here to here. It's just y. Right? So isn't this going to be 2 times y times how thick it is? I can't have y in a dx problem, though. So I have to take this and solve this for y. It's x squared. This goes right here. So it'll be 2 times the square root of 4 minus x squared. Squared, right? So I've got, this is what it'll be. Just rewrite it. This goes from -2 to 2. This is going to be 2 times the square root of 4 minus x squared. That's the base. That's the height. There's your thickness. Chase, you okay? I would like you to do, please, for the block day. Page 4, 28, 18, 43, 59, 66, page 4, 37, 6, 8, 15, 18 through 22, even. Hey guys, listen, I know that you had questions on the homework. I was hoping that I hit them on the warm-up, but this is setup only, by the way, right? So don't, just like you've been doing. Tomorrow morning during advise, I'll be happy to work whatever I haven't gotten to. Like if something's still bugging you, come by in the morning and I'll take the time to work through all that stuff, okay? I won't have any problems ready, so I'll do whatever you guys need me to. All righty. Any questions before we get out of here?